slice helical CT and multi-slice helical CT. So the clinical advantages of multi-slice CT is increased speed, shorter acquisition times with lesser motion artifacts, high axial resolution with thinner slices in the longitudinal axis, retrospective creation of thinner or thicker sections from raw data, accurate anatomical 3D reconstruction, especially in angiography and virtual endoscopy with lesser helical artifacts, increased volume coverage per unit time, reduced partial volume artifacts and noise, detailed multiplanar reconstruction images, and use of lesser contrast materials and delivery of contrast material at faster rate, thus increasing contrast enhancement in images. So we have multi-dimensional or multifactorial advantages with the multi-slice CT. So it is fast, larger volume is covered in lesser time, and artifacts are reduced, image noise is reduced, and we have more information as we have multiplanar images available, and the final reconstructed image will be more clear, concise, and having more information about what is actually happening, or more visually appreciable of minute details inside the body. So applications of multi-slice CT, there are musculoskeletal applications. One second. So the applications of multi-slice CT, they have multi-dimensional and multifactorial applications also. The musculoskeletal applications include with isotropic acquisitions, with narrow collimation, low pitch, high MAS. The quality of multiplanar reformations obtained is very high. And CT angiography, long coverage possible without sacrificing spatial resolution, and cardiac scoring, brain perfusion, virtual endoscopy, coronary angiography are other applications of multi-slice CT. And this has several advantages over standard CT, the spiral CT. So we have seen in brief. So in order to see the speed, the most important one is the speed. Since the patient is moving continuously through the scanner, the duration of the exam is markedly shortened. The entire chest or abdomen can be scanned in 30 seconds, usually during a single breath hold. And improved detection of small lesions. Spiral CT can be performed during a single breath hold. Contiguous slices are truly contiguous. And also, since a volume of data is obtained, the spacing of the acquired slices can be manipulated after the scan is completed. So we have three-dimensional data acquired in multiple directions. So we have the volume of data which is obtained. So this can be processed after the scan is completed to get more desired information out of the bunch of data which we have acquired during the protocol. And this allows detected lesions to be placed in the middle of the slice, which creates a more accurate image of the lesion. And another advantage is improved contrast enhancement. So IV contrast is often injected during the CT scan since spiral CTs can image a region of interest in such a short period of time. The injection of intravenous contrast can be timed to ensure optimal contrast enhancement and improved evaluation of various organs and blood vessels. Also, the speed of injection, the speed of IV contrast also can be controlled as desired for the particular study or particular protocol under consideration. So, which will enable us to have much more contrast enhanced images. Another is image reconstruction and manipulation. So we have lot of data now, which is acquired in all direction, which is contiguous, which is acquired in a very short period of time. The volume of data obtained through the spiral CT can be manipulated in many fascinating ways by powerful computers connected to the scanner. The transverse image can be reconstructed in any plane and three-dimensional images be formed and moved into any position. A surface view of the body can be created and then skin, muscles and overlying organs can be stripped away. And contrast enhanced vessels can be isolated and converted into CT angiograms. So the image reconstruction and manipulation is also much advanced when it comes to spiral CT or helical or spiral multi-slice CT. So we have added advantages of powerful computers and a lot of data which is acquired, and from that whatever information we needed can be extracted and it can be strengthened further to get more information or more clear idea about what's happening, or the not required information which is acquired can be subtracted from what we need to look at. So from a bunch of data, large amount of data, we can choose whatever we require and look at it more closely and precisely. And the technical data for helical scans, the fundamental step in helical CT technology is the introduction of slip ring technology. So advantages are continuous stable movement, no interscan delay, and image reconstruction at any position or interval. So this is the one major advantage of this helical CT with slip ring technology. And large volume coverage in single breath hold, no interscan delay, and from images, form images by synthesizing projection data via interpolation. So whatever data we acquired, it is continuous with respect to the patient body movement, and there is no delay between acquisitions, and we can have the image reconstruction for any position or at any point of time. And since the CT, the X-ray tube and the detectors are rotating around in spiral form with the help of slip rings, there is no interscan delay, and the whole area which we needed to image could be completed within a single breath hold, less than 30 seconds. So that enables to remove some of the artifacts which may be possible due to the internal motion during the study, which we have no control over. And this data could be synthesized for required image formation as we require for the particular study, what exact information we need from the study. So that could be achieved by synthesizing the data which we acquire, and if required, interpolate between the data from slice to slice, or from whichever the transverse plane or axial plane or longitudinal plane, whichever plane we needed, and in different directions or different angles. So today's CT system is typically a third, fourth generation with multi-slice spiral scanner. So parallel fan and cone beam CT. After all of that in parallel beam CT, still have acquired only one slice of the patient. Then needs to be repeated for each slice after translating the table. That is why parallel beam CT was replaced with fan beam CT. So the first generation CT based on small parallel pencil beams, and they were very slow, requires translation of the X-ray tube and detector for every pencil beam. So each of the beam, the X-ray tube and detector needs to move in the parallel way or translate in the linear way, and also rotate to acquire other slices. And fan beam, you can see the fan beam geometry over here. So this is fan beam CT was introduced in the third generation, and reason it is called fan beam is because the beam coming out of the X-ray tube makes the shape of a fan. You can appreciate that this one looks like the leaf of a fan. And these are significantly faster scanning than parallel geometry, started with third generation CT. Geometry is approximately 16 slice or less than 1 centimeter at isocenter or fan beam, and can use helical or axial scanning but takes many rotations to cover the anatomy. Each rotation in fan beam CT provides just one slice. Therefore, many rotations are needed to cover the full anatomy. This is where the cone beam CT comes in for even more acceleration in the speed of acquisition. So cone beam CT. So fewer rotations needed than cone beam CT. You can appreciate between this is the fan beam, and here we have a cone. 1, 2, 3, 4. You can appreciate it. This becomes little more three-dimensional. So fewer rotations are in comparison to this. Fewer rotations are needed for the fan beam than compared to the fan beam. And options for coverage at isocenter is up to 16 centimeter in one axial rotation are available. Also, CT performed on interventional X-ray and radiotherapy systems is inherently cone beam. So this came after the fan beam geometry, and geometry is the same as third generation CT, that is an X-ray source and X-ray detector mounted straight across one another. Detector has many more rows, so the shape of the X-ray beam coming out looks like a cone rather than a fan. Cone beam CT is basis of modern CT scanners, and it is also called multi-detector CT. So it is not because of the detector alone or the beam geometry alone it is called multi-detector CT. We have seen why it is called multi-detector CT in the previous slides. And whole organ can be scanned in a fraction of a second. So this is all the geometries in one slide. So parallel beam, the beams are parallel to each other and they are linear. Each rotation slow. Many rotations are needed for the complete acquisition. And fan beam, each rotation is faster compared to the parallel beam, but still many rotations are needed for the complete acquisition. And cone beam, each rotation is fast and few rotations are needed as larger area will be covered in one go. And to discuss about filters, the filters are placed between X-ray source and patient, removes the low energy X-rays, produces a more monochromatic beam, may be bow tie shaped to even out attenuation once it passes through the body. And let me ask you, how many types of filters are there in an X-ray tube? What are the types of filtration in an X-ray tube? Yes. What is inherent?
Due to tube housing of that X-ray tube,
Yeah. And added?
we add copper aluminum filter in it.
Yeah. Yeah. So similar here also, and this so whatever disadvantages are there or whatever deficiencies are there with the X-ray system, that could be replaced with more advanced or more sophisticated filter systems in CT scanner. One is that of bow tie shape, the tie which is like a butterfly. So that could help in achieving the equal intensity levels after the beam is passing through. So we know the center part of the patient will be thicker, so the filter will be thinner in the center, and towards the sides it will be expanding, and of the incoming intensity, the incoming X-rays after passing through the filter and after passing through the patient, once it reaches the film, it will all have uniform intensity. So we have seen that the purpose of filtration is to remove the low energy X-rays. So inherent filtration is because of the hardware of the machine, like whatever X-ray glass housing is there inside which the vacuum is there. So this glass through which the X-rays has to pass through, so it will attenuate or absorb very low energies and attenuate little higher energies, and does not affect the much higher energies in the X-ray spectrum. So still there are low energy X-rays which are not contributing positively towards the image formation, or it will act as noise or fog in the X-ray film, and also add radiation dose to the patient. So they need to be removed. So that is why we add added filtration and produces a more monochromatic beam. What do you understand by monochromatic? Anyone?
Single wavelength.
Yeah. So it will have single wavelength. So that the mono means single, chromatic means color. So this enables us to have to remove the other wavelengths from the incoming X-ray spectrum. And then there is collimators. This is placed between the filter and patient, narrows beam to produce thinner slice and less scatter from outside of the slice and lower patient dose. This is one of the important things we need to utilize in our daily life. So if the field size required to cover the desired area which we need to image is less, then we should collimate the field opening. So if we are opening it more, it will deteriorate the image quality by the scatter radiation from the extra body part which is getting exposed. Also, that will give undue radiation dose to the patient, as that we are not concerned about the imaging of that area. Hold on a second. Yeah, and collimation is all the more important when we do pediatric imaging. You know, when we open the normal field sizes, normal collimator opening, the whole patient will be encompassed in that. So that will add more radiation to the pediatric population. So if we want to do a chest scan, then correspondingly we have to collimate the beam to encompass only the chest area of the child, so that the radiation dose to the child will be much lesser, significantly lesser. And the detector arrays, so the different types of detector arrays, like the solid state detector arrays were the most commonly used, and solid scintillation layer converts X-rays into light photons. We have seen that. What was the scintillator material in the detector, solid state detector? Anyone remembers? It was sodium iodide. So sodium NaI. So the sodium iodide is a scintillating material. When X-rays falls on it, it produces light photons, and these lights are detected, and then they are amplified by a photomultiplier tube to get a strong signal out of the system. And ionization chamber detector, they are no longer used. These are gas. Yes. Pre and post matlab? No, I'm not understanding what you are trying to ask. Collimation means the field size you open for, or the lighted area, no? On the patient body surface, you see light while you position the patient, right?
Ma'am, in some books it has been written like pre-patient collimation and post-patient collimation.
Okay. Post patient collimation. Can you please something more about it? What is written over there?
Yeah,
And
ma'am.
these are used for slice thickness.
Okay. Just a second. Pre and post patient collimation.
Yes, ma'am.
In which book it is?
In Christiansen also it has been mentioned.
Okay. 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 So the post patient collimation, it is not after and before, it is the actually at the same time where we are placing the collimator. So there can be one collimator which I am talking about, no, like on the X-ray tube head. When the on the X-ray tube head, how much the tube, how much the collimator you will open to access the area on the patient surface. That is the field size. Field size which we open. Like you open 10 by 10, 15 by 15, 20 by 20, 30 by 30, like that, no, to encompass the area to be imaged. You understand? On the
Yes, ma'am.
X-ray tube head. So after the focal spot, the X-rays are coming in a conical shape. So uh, we have the radio opaque material uh, in the form of slabs which are placed. These are called collimators. They can be opened or closed according to the requirement of the area to be covered in the image. So that is called post collimator, post patient collimator. And the pre patient collimator is if we are keeping some filters in addition to the added filtration to reduce the, like the bow tie filter we were talking about, no? So in addition to the normal added filtration which is available with the machine. If we are adding additional filtration to reduce the patient dose or the area of the patient to be imaged, so that is again called, that is called pre-patient collimation. I think you understood that. So the post-patient collimation is about the collimator on the X-ray tube head. Along with the X-ray tube, there is collimation provided. So that is called post-patient collimator. So how much area the X-ray beam falls, that is decided by this collimator. Understood? And pre-patient collimator is like a filtration. Added filtration is there. So if we have a designated filter which will enable to limit the area of the patient being imaged and reduce the patient dose, so that is called pre-patient collimator. Pre-patient collimator is nothing but a filter. Post-patient collimator is the collimator which defines the area to be imaged. Got it?
Yes, ma'am.
So this is detectors. Detector is something again below the patient, right? So these things are above the patient. One is at the X-ray tube level and the another is between patient and the filter.
Ma'am,
Yeah.
ma'am, in MSCT, it has been said that we don't use post-collimation because slice thickness is decided by detectors.
Yeah, that different things depending upon the requirement and how much X-rays we need and what study we are conducting. Accordingly, each protocol is set. No, you don't set all this. So for a particular procedure to be carried out, we select the protocol for that particular procedure, right? Say CT angiogram we have to do. So we select the CT angiogram protocol. So in that it will all come into place accordingly. What is required, what is not required, like that.
Okay, ma'am.
It depends on what information we need to get out of the study. So some places we need to highly reduce the X-ray field. There we will use, like in a static image, if we are taking it, this is more applicable when we are doing the X-rays mostly. So that is there. And in when we are coming into multi-detector, multi-slice CT, then we do not have that issue at all. No, we are taking small slices and the whole thing is completed over a very short period of time. So it is, we know two places are overlapping each other. If we are applying the correct pitch, then there is no overlapping, or it is not like how we apply this thing. So that is why it is not used in the multi-slice CT or MDCT.
Ma'am, it means like
That,
in MSCT, we are requiring a whole volume. Then we are reconning in different slices we want.
yeah, we don't need this collimation over there. No, it is in a circular
Yes, ma'am.
form. It is rotating around. So whatever the field opening is there at the X-ray tube, that is only there.
Okay, ma'am, now understood.
Yeah. And gantry has slip ring system, allows continuous rotation of the gantry. So this is again another slice summarizing the first 5 generations. First generation, translate rotate with single detector. Second, translate rotate with row of detectors. Third is rotate with continuous rotation of a row of detectors. And most commonly used CT type is this. And modifications are made, like whatever problems were there with the third generation, they were removed by adding additional technology. And fourth, rotate fixed with complete ring of fixed detectors. And fifth is electron beam scanner used in cardiac imaging. So Sixth and seventh are combination of third, fourth, fifth, and some additional computational hardware and software. One second. What? No, no. We are using the image, the raw data which is acquired will be processed to produce the images. So in grids, we are keeping the grid inside to reduce the scatter radiation. So in CT scanner, what we commonly do is after the data is acquired, we process that data, the back projected data and all to get the right image. No, CT, what is the KV? We have discussed this. What is the KV used in CT? Maximum KV used in CT. Yeah. It is 120 we are utilizing for the protocols. It can be up to 150. That is the same case in X-rays also. So the technology grid, the use of grid is another problem with the, what is the disadvantage of using a grid?
Patient
It
dose
will cut off
increase.
the primary radiation. The grid will cut off the primary radiation also. So the primary useful radiation passing through the patient will be less. The intensity of the radiation passing through the patient when we are using the grids are less. So in order to overcome that problem, what we will have to do, we will have to expose for more radiation. So that will give rise to added radiation dose to the patient. And it is not with the energy of the kV of the this thing we are utilizing grids. The purpose of grid is whichever scattered radiations are there, which is not in the direct parallel to the incoming primary radiation, they needs to be removed, right? That is the purpose of grid. We do not
Yes, ma'am.
want some rays which is having information about some other place coming and falling in another place and telling, okay, which information is correct. So if we take, say, the 3-3 matrix, in the full 4x4 matrix, 3x3, that square if we take, so we want only the information corresponding to that particular matrix. But if there are scattered radiation coming from 1/2 and falling into 3/3, then the quality of the information in 3/3 will be reduced. So we do not want that. We do not want the scattered radiations which are not falling parallel to be reaching the imaging plane. So that is why we are using a grid. So when we are cutting off that, so the primary radiations are also being cut off. So then correspondingly, we will have to increase the initial exposure, giving rise to more radiation dose. So this is the basic fundamental principle of grids. So we can use different techniques to take the advantages of grids with respect to the image formation and get a good quality image. So mostly what we do nowadays is we give much lesser radiation exposures, much lesser KVPs and MAs, and we have advanced computational softwares to remove the unwanted information from the collected data on the photographic film or the imaging plane. And now that I remembered, yesterday we were talking about the slip ring, what it is made of. So it can be made of any conducting metal. So the examples could be copper, aluminum, brass, all these or a combination of these. So this will be the criteria should be the material should be strong, durable, and resistant to wear and tear, because the system, the X-ray tube and the detectors will be rotating multiple times in the slip ring. So that motion should reduce minimum wear and tear, so that the equipment can have a longer life, and it should be strong and durable also. So these things are the primary requirements for the materials to be used for making a slip ring. And it should conduct the electricity between the ring as well as the detector and X-ray tube. So it should be, it will be a conductive material, and which has the qualities like strong, durability, and which can withstand wear and tear. All these are the materials which can be chosen. So copper, aluminum, brass and combination of mixture of all these also can be used. That would be like one particular manufacturer can utilize their own particular combination of the material to make this. So image reconstruction is the one of the most important things, especially when we are talking about all this. So when a source detector makes one sweep across the patient, internal structures of body attenuate the X-ray beam according to their mass density and effective usage. And once more, I wanted to tell you, CT and X-rays, the KVPs used are within the same range. The maximum capacity for which an X-ray machine is made, or an X-ray machine is made in X-ray tube is made in the CT, both are of same range. And are there any other CT X-ray tubes which are made for lower energies? Any examples?
Mammo tubes.
Yes. Mammo tubes, dental tubes, all those are much lower capacity ones. Otherwise, CT and X-ray, the normal CT and X-ray tubes are made in the same this thing. And very recent and very new X-ray tubes are there, which are producing much, CT tubes are there, which are producing much lesser X-rays. But we need to have much advanced software or image reconstruction to get, see, our optimization is how? We need to have a good image. We need to identify bone as bone, hair as hair, tissue as tissue, different tissues separately. So how much ever possible with respect to that. So what minimum KVP can achieve reasonably good image, that is our optimization between. So if we give 150 KVP, we might get better delineation at some places. So that is not, but if we can get the clinical information which the physician needs with lesser KVP applied, we will apply lesser KVP. So that principle does not change. So in the very newer or most advanced CT machines, the maximum applied KVPs are much. That will not give us the optimum quality image with the normal reconstruction and image processing softwares. So there we need advanced softwares to enhance the image which was acquired. So there will be more of noise and less of this thing. The image will be less good quality. So whatever image we got, we have to enhance those images to be reasonably useful for the visual inspection of the physician. So that is done nowadays. Reduce the KVPs and image processing or image reconstruction is done with advanced software system to enhance the quality of the image which is acquired with lesser radiation dose or with lesser KVP applied. And
Ma'am,
intensity of radiation, yeah.
somewhere I've
Yes.
read that detector collimation act as a grid in CT.
See, that is what I'm telling you. Don't, grid is what? Grid is you have a thick radio opaque material and a radiolucent material placed in series. That is what is a grid, right? And
Yes,
the
ma'am.
radio opaque material will block the radiation from passing through, and the radiolucent material will pass the X-rays. So whichever radiations are falling in straight lines with the grid, the radiolucent material will pass through. And if one beam is at an oblique angle of incidence with the grid, then it has to pass through the radio opaque high density material. So that will block that radiation. It will not reach the imaging plane. So that is what I was telling. It is not by utilizing the grid, like if you ask me, are we placing those? We are not placing those. No.
Yes, ma'am.
We are manipulating the system such that we are getting less and less of slanted X-rays while imaging and more of straight X-rays. And even after acquiring that information, we can reduce the slanted or scatter X-rays by doing multiple image reconstructions.
Yes,
So
ma'am.
whatever the scattered radiation component was detected, that could be identified and removed in the image reconstruction phase. So the basic principles are all same. We have incoming X-rays coming, then we have the patient, then we have the photographic film or detector. So there are problems. Patient we cannot change. Can we change the patient?
No,
If the
ma'am.
patient is broad, the patient is thick, the patient is big, we have no control over the patient. We cannot change any of this thing. Like in mammography, we have the option of compressing the breast tissue in order to make it homogeneous. But that option is not there in CT or X-rays, right? So what we can adjust is, okay, we want to remove the low energy X-rays, which will scatter more and give more radiation dose to the patient. So in order for that, we have multiple options. How can we remove those? There can be machine related factors. There can be imaging related factors. So we will choose and apply whatever is required to get the optimum information which is required out of the study. So intensity of radiation detected varies according to this attenuation pattern or projection is obtained. These projections are not displaced visually, stored in digital form in the computer, and computer processes the projections to reconstruct an image of anatomic structures within that slice. So a lot of things happens in image reconstruction also. The softwares or the algorithm which we used to use previously had limited options, but nowadays we have lot of options to increase the image quality, at the same time reducing the exposure parameters. So if we want to reduce, see, like automatic exposure control is there. What is automatic exposure control? Anybody? So in simple terms, it is like when we have to, for a particular patient of a specific weight and height and thickness, we need to apply, say, 85 or 60 kVp. But the program which we selected has a standard built-in set kVp as 90 kVp. But in order to get the good image for that particular patient, it does not require 90 kVp. It can be done with 75 or 60 kVp. So then the system itself will automatically reduce the applied voltage, applied kVp. So that is it is mostly used in CT and fluoroscopies, where as required, the KVP will be chosen by the system. It is called automatic exposure control. So this will also act as lesser of scatter radiation, more of primary radiation, less radiation dose. These are all interconnected. So how you achieve your whatever is optimal for your particular study, your particular patient is what is important. So that it is all based on the fundamental principles which are going to be same. There is nothing going to change. So in the generations also, that is what I want you all to understand. In the first one, we had parallel beam. In the second one, we had and parallel beam with the detector and detector and the X-ray tube arranged parallelly. In the second one, we have detector sets there, more detectors, and also the fan beam. And later we have cone beam, and we have a ring of detectors. Then we had the circle of detectors. So these are all developed according to the need. Whatever problem was there with the initial one, the imaging was good with parallel beam, but the problem was it was taking too much time. So then we will have to use the fan beam and cone beam, and then multiple detectors to acquire more information so that lesser time will be utilized. And then this more detectors were causing artifacts in the image. So in order to overcome that, instead of moving the detector, we started to have the fixed detectors in a circle. So whichever direction the X-rays goes, we can detect it and we can process it. So then we realized that more than that, these artifacts could be removed by other methodologies, but the cost involved in producing the ring detector and the quality of image which are produced. So considering that, in order to further fasten the process, the slip rings, like the circulatory helical scanning came into picture, then the slip rings came into picture. So it made further acceleration in the time for which the imaging was done. And some of the old machines used to be very huge. And we have seen that in one of the electron beam, this thing like where the water bath is placed around the patient. So these are all will produce claustrophobic also. So we are looking at faster acquisition. Why faster acquisition is required? Not only because of the internal motion. It is for the patient comfort also. That is also comes into picture. We need to ensure that patient can comfortably lie down for the scan without much difficulty or problem and get the image also. This is also needs to be ensured. So the sizes of the machine became bigger, the bore of the CT scanner became bigger, so patient need not be feeling the claustrophobia, and more comfortable. Children also can be placed more comfortably on the machine. All these things also comes into picture. So that is what I was trying to tell you all. We utilize and select and choose whatever we require to get good quality image, visually appreciable, to identify the disease condition and manipulate all the parameters which can be manipulated accordingly. So after the image information is stored from the particular slice which is imaged, individual values of the matrix elements are obtained, and matrix of values that are obtained represent cross-sectional anatomy, and dedicated array processor is used to do calculation and instantaneous image display. So this is a schematic diagram of CT image formation. Scan parameters are set. X-ray tube rotates around the patient to collect the raw data. Pre-formatted raw data. The raw data are values of all measured detector signals after the scan. convolution with filter, image reconstruction algorithms, back projection of convoluted data, and reconstructed images of CT numbers, and image storage, display, recording, and archiving. So we can change the scan parameters, we can change the X-ray tube performance parameters, and whatever data acquired can be reformatted according to the information which we receive from the scanner, and then that can be reconstructed using convolution with filter, and image construction reconstruction can be done by using the softwares, and this information can be stored in terms of CT numbers, and the CT numbers, depending on what CT number is in which, that is intensity information, basically grayscale information or color scale information. So accordingly we will get the visual image. Image reconstruction is a mathematical process that generates tomographic images from X-ray projection data acquired at many different angles around the patient. The reconstruction process is based on use of an algorithm that uses the attenuation data measured by detectors to systematically build up the image for viewing and interpretation. Image reconstruction has fundamental impacts on image quality and radiation dose. So this is another very important area where a lot of research and development is happening to reduce the radiation dose while improving the image quality. So the algorithms are defined as the set of rules or directions for getting a specific output from a specific input. So algorithm must always terminate after a finite number of steps. Algorithms can be represented in form of flowchart, listing the series of steps combined all together by programming language like C++, Java, etc. to form a software to do a specific job. CT reconstruction algorithms converts each attenuation coefficient values obtained, splits it into intensity and location at object, forming an image with specific grayscale. So all these processes are done in reconstruction also. And there can be iterative technique. What do you understand by iterative? The algorithm will repeat itself again and again. And back projection, whatever data we collected, the back projected image of that will be taken as the primary data. And filtered back projection is where we remove some of the information from the back projected data and utilize that for the final image formation. They are basically a mathematical algorithm that takes the projection data and reconstruct cross-sectional CT image. Modern scanners use filtered back projection image reconstruction. So filtered back projection means you are filtering but not using the filter which we are discussing, like the hardware filter. So iterative method, the original method used by the G. Hounsfield, and starts with an assumption that all the pixels have the same value. Assumed values are compared with measured to collected data, and collections are made in assumed values so that the assumed and collected data come closer. It is slow and takes longer computer time. Data must be collected before reconstruction. So these are different examples of how the iterative reconstruction technique is done. So each pixel will have defined values from the image acquisition which happened, and in order to understand. So the image processing or the image reconstruction needs to understand the data collected. So they try to understand, match it with whatever standard steps are there, then whatever, whether it is negative or positive with respect to that, higher or lower with that, all these comparisons will be done and the final values will be assigned and interpreted. So different examples are given here. So here is an example of what is exactly a back projection. So the mathematical process based on trigonometric is back projection. In this method, required projections of an object are obtained by multiple scans, and then the projections are back projected to produce the image of that object, and back projected image receive density contribution from neighboring structures and creates noise. So image quality is very poor and large number of projections are required to improve the image quality. We will get blurred images, so not in use. So here we have lot of noise present, so we need to remove the noise. So filtered back projection. So similar to back projection, raw data are mathematically filtered. So this is one important terminology, mathematically filtered before being back projected. The filtration compensates the sudden density changes that causes image blurring. Inside margins of dense areas are enhanced while the central region is repressed. It reverses the image blurring and restore true image of the object. So filtration change, the intensity can be reduced, energy can be higher. So this is the basic, this again it is the basic fundamental with the filtration. So intensity will be reduced because some of the rays will be cut off, and energy or the average energy will be higher because low energies will be cut off. Filtration material, special filter in CT, bow tie to make the beam harder and more monoenergetic. Attenuation across filter, attenuation across body. This is the pre and post filtration which we were talking about. So this is a bow tie filter. So this will give us a X-ray beam intensity like this. And then we have patient. So here you can see this is collimator. This is again collimator. So
Yeah.
this
Ma'am, we are
defines
talking
the,
about this only, pre-patient and post-patient.
yeah. So this is how the machine schematic will look like. And this is how it actually functions to get the good quality. So we have the anode is made of tungsten and molybdenum. Focal spot, CT utilizes different focal spot, small focal spot and large focal spot. Smaller focal spot for sharper images, and CT large focal spots are 1 mm are used at high power rating up to 60 kilowatt, and the small focal spot are 0.6 mm is used at low power ratings about 25 kilowatt. And MA is tube current, the number of electrons flowing from the cathode to the anode, and KVP is the potential difference between cathode and anode expressed in kilovolts, and S is the time of exposure in second. MAS is the tube current of certain length of time. So X-ray production results in a lot of heat and very little X-rays being generated. So heat unit is another terminology. How we calculate that? HU is the product of KVP, MA and time. So most CT tubes have heat capacity of 3 to 5 million HU. So have you ever seen a heat unit chart?
Tube rating chart.
Yeah.
Yes.
Yeah.
Yes,
So
ma'am.
this is same here also. See, whatever is the principle is there in X-ray, that same thing is here also. Here also we have the X-ray tube, which is same as the other X-ray tube, right? We are producing the X-rays, letting it pass through. The acquisition is changing. So how much KVP can be coupled with how much MAS for the safe implementation or safe application is what is taken from the tube rating charts, right? The capacity of, if we are selecting one particular KVP, how much we can go with MAS, that information we get.
How,
Or
how much
yes,
exposure is safe? That how much exposure is safe
safe for what?
for doing the procedure?
No,
At
safe
what?
for the
At what?
machine.
Yes, yes.
Yeah, that is the difference. So how much exposure is safe for the machine? If I am taking 75 kVp and I am taking 15 MA, and if I am taking 20 seconds, the machine will burn off, right? So
Yes,
if
ma'am.
corresponding to each kVp, how much maximum MA can go, or for a particular MA, how much maximum kV I can go. That information is there in the chart. So
Yes, ma'am.
correspondingly, and nowadays we are not manually selecting. Olden days, like 40 years before, for a particular, like if we have to do a chest examination, we have to select the KVP and MA and S and all manually. That time this charts used to help. So now we select thorax and all the parameters will be automatically selected. And in fluoroscopy, CT and all, we have automatic exposure controllers which will further help in reducing the applied parameters. So if we increase KVP, intensity will increase, energy will increase, right? KVP
Yes, ma'am.
corresponds to what? The speed at which the electrons are drifted between the cathode and anode. That is the KVP. If we increase the KVP, the speed of the electrons will increase. And more number of electrons will hit the target at the desired energy level, desired speeds. So more number of X-rays will be produced with higher energy. If so, that is the idea over here. So reduction of heat units technique, the compensation technique is used, and KVP, MA and time will increase the noise. And KVP range is 80 to 140, too low of KVP increase noise. So when the KVP is less, energy will be less and noise will be higher, but because not enough penetration of the patient. And this condition is called photon starvation. If sufficient number of photons with higher energy are not passing through the patient and falling on the photographic film, we will not have a good quality image. And whatever information will be there will be most of hazy and not useful. So then we will have to increase the kVp if that is the condition. And tube current change, increasing current will increase intensity and energy, no change. So intensity means, so when increase the tube current, what will happen? More number of thermionic emissions will happen. Tube current is what controls the number of electrons. So increasing the tube current, we will have more number of electrons and correspondingly more number of X-ray photons. But the energy of the photons will not be affected by increasing the MAS. So why we need to change MA or time? To avoid motion, reduce the time, and pediatric technique modification, and reducing noise. To reduce noise, we will increase MAS. So you can see the quality of image here, artifacts. This will be how noise artifact will be looking like, and this is how the motion artifact will be, like streaks of rays. So I think this is the last slice of this. So we will not have class in the next week. Probably if we can have one on Friday or Saturday, next Friday or Saturday, I will let you know. Otherwise, we will not have. We will have next Tuesday only, the week after that. So I will send you this PPT also today. Meanwhile, you go through all that and try to understand the fundamental principle, because that is what not going to change, and then see how things are modified, altered, or in other terms manipulated to get the desired results. And we will discuss those before we start the next topic in the next class. Is that okay?
Okay, ma'am.